Okay, so last part of section 11.2, we're still looking at a series, which means we're going to be adding up a bunch of numbers, but we're going to focus on an infinite series. So yesterday we talked about finite. What is the word finite? It ends. Right? If I say you have a finite amount of time to take the test, finite means you have a certain amount of time, you don't have an unlimited amount of time. It's going to end at some point, your time. Okay? So finite has an end to it. Infinite goes on forever. Now, if you think, well, how can you add up numbers that go on forever and actually get an answer? Well, sometimes you can, sometimes you can't. It depends on the kind of numbers you're adding up. So we'll look at both cases. If you can't add them up, there's a name for it, and that's all you would write. If you can add them up, there's a name for that too, and then you actually give me an answer. Okay, what does it add up to? So we'll look at both. And that's what I just said. The only way you can add up an infinite amount of numbers and actually get an answer, like 6, is if each number that you're adding is smaller than the one before it. Take, for example, 2 plus, let's go like this, plus 1, plus a half, plus a quarter, plus an eighth. And I put a dot, dot, dot because it keeps going. What am I doing to the number each time?
Decreasing, subtracting from it.
No, not subtracting. Multiplying it by a half. So what's happening is each time you're adding a number, you're only adding half of what you added before. And eventually, if you keep taking half over and over and over, the number gets so small that it gets very close to 0, what you're adding each time. And it's almost like it doesn't even make a difference anymore. Okay, that's the idea. If you had numbers that did the opposite of this, let's say 2, 4, 8, 16, 32, numbers that doubled each time, they're just getting bigger and bigger and bigger. So if you add them up, the answer just gets bigger and bigger. It doesn't add up to anything. It just approaches infinity. All right, so that's the notation that we use to represent an infinite summation. The only difference between this notation and the one from yesterday is that symbol at the top. It's not an n anymore. N means it's finite. It stops at a number. The infinity symbol means it goes on forever. The other way that I'm showing that in expanded notation, which is on the right, is right there. Dot, dot, dot. Because there's a dot, dot, dot at the end, it means it keeps going. All right. If this was the kind of problem we were doing yesterday, what I circled in red, these 3 dots, wouldn't be there. Neither would this plus sign. It would stop at the nth term, and it wouldn't go any further. Today, it keeps going. Okay. So any question on the sigma notation for an infinite sum, which is on the left, and then expanding it out, which is on the right? So you can't add an infinite number of terms by hand. Okay? It's impossible, right? There's infinitely many things to add. It's going to take you a long time. So you got to come up with a better way to do it. We're going to look at it 2 ways. We're going to look at it using a formula, but I'm also going to look at it by graphing something on the calculator. And what we can do by graphing it on the calculator is we can look at the sum and see, all right, what happens further and further away? Is it approaching a number? Okay. Does anybody remember what that was called? If you had a graph and it gets closer and closer and closer to something but never reaches it. An asymptote. That's what we're going to look for. So if we can graph the sums on the screen and it looks like an asymptote, like they're getting closer and closer and closer to something, but never reaching it, then we can say, all right, it looks like it would add up to a number. If it doesn't look like there's an asymptote, that's different. Okay, we'll talk about that after. So if there's some number that when you graph the horizontal line, y equals that number, and that is a horizontal asymptote for whatever sequence you're adding the stuff up in, then we say that that sequence converges. Okay? That's what it's called when an infinite amount of numbers add up to something. They converge. Or you can also say the sequence is convergent. So let's say you graph the line y equals 4. Be a horizontal line like that. And then let's say you're adding up some numbers, and your graph looks like this. Okay, what's happening there is when you start adding up some of the numbers, it makes a big difference. But then later on, the numbers that you're adding are getting so small, they don't make a difference anymore. So what's happening is you're getting closer and closer and closer to a horizontal asymptote. That's an example of what a convergent sequence would look like if you draw it. And it converges as you approach infinity. Okay? So the further you head to the right, the closer and closer and closer it's going to get to the asymptote. Now, just saying that it converges that means it adds up to something, that's not enough. You have to tell me what it adds up to. Does it add up to 6? Would it add up to 7? What's it add up to? Well, it adds up to S. Okay? It adds up to whatever number is the horizontal asymptote. That's what it's getting closer and closer and closer to, but never reaching. Okay? That's saying the same thing I just wrote up above, so don't worry about that. All right, so what we're going to do is we're going to look at a sequence, and we're going to see what happens if we add up like the first 3 terms, okay, by hand. And then we'll look at what happens if we add up the first 4, the first 5, the first 10, the first 20, okay, and see if we notice a pattern. Okay. And I think you will. All right, so I want to add up every term in that sequence from 1 to infinity. And here's the sequence that's going to generate the terms I'm adding up. 2 times 1/3 to the k minus 1. Now, obviously you can't go to infinity. But what you can do, though, is look at some of the partial sums on the way there. Let's look at what happens if we add up the first 4 terms. Then let's look at what happens if we add up the first 5. And then let's look at what happens if we add up the first 6. I think you'll start to notice a pattern pretty quick. So yesterday at the end of class, we had a formula that could calculate the nth partial sum for a geometric sequence. And we just went over one in the homework too. Can someone remind me what the formula was?
1 minus r to the nth power over 1 minus r.
Yep.
Doesn't Hager go?
Yes, and then there's a sub 1 in front of it. Yep. Okay. So a sub 1 is your first term. So we'll figure that out in a second. R is right there. Okay. 1/3. So let's figure out the first term. So plug in 1 for k. What's 1 minus 1? 0. What's 1/3 to the 0 power? 1 times 2. 2. So really, if you want to look at that and find your first term, it's right there. Always. The first term is always the number in front. R is always the number that's in the parentheses. So now we're going to fill in those 2 numbers, and then we'll do n equals 4. We'll start with that one, see what we get. So the first term is 2. I already did this out. R is 1/3. I already filled that in. And if you type all that in on the calculator, you get an answer of 2.96. That means if you manually found the first 4 terms in the sequence, okay, we manually found the first one, it was 2. But then if you found the second, the third, and the fourth one, and added them all up, you would get 2.96. Does anybody want me to show you how you type that in on the calculator?
Sure.
Okay, so you just have to be careful with your parentheses, and I would do it in 3 steps. Let's start with 1 minus 1/3 to the 4th. 1 minus 1/3 to the 4th. That's the top. Okay, I didn't do anything with the 2 or the bottom yet. Now, take the top, divide it by 1 minus 1/3. I know 1 minus 1/3 is 2/3. So I could have just done that in my head, but I'm trying to show you how to use the calculator to do the whole thing. Okay. So there's the top divided by the bottom. Now multiply it by 2. And that's how I got 2.96. That's how you'd want to type it in. Could you do it all in one step? Sure. You don't have to do it in 3 separate steps. But you got to be really careful with all your parentheses, and there's a lot of stuff. Okay, so that's what you get if you add up the first 4 terms. Here's what you get if you add up the first 5 terms. Okay. First term is still 2. R is still 1/3. We change that number because n represents how many terms you're adding up. And if you add up those, you get 2.9877, roughly, okay, rounded. So just by adding up the first 5 terms, what does it look like they're getting pretty close to? 3. Okay? It's not like you need to add up the first 700 terms to see what it's getting close to. If you add up the first 4 or 5, you can already see it's getting close to 3. And then I did the 6th, and that gets even a little closer to 3. But look how small the 6th term must be. When you added up the first 5, you got 2.987. The first 6 is 2.996. So that you didn't add a very big number to get from here to here. And that's the key. The number that you're adding each time is getting smaller and smaller and smaller. Okay? If you added up the 7th term, it might be like 2.999, or even closer to 3. But it's never going to reach it. Any questions on that? So technically, did I really add up an infinite amount of terms here? No. What I did is I looked for a pattern. I added up the first 4, the first 5, the first 6, and I'm kind of thinking, well, looks like it's getting close to 3. So if I kept adding them up forever, it would probably get close, even closer to 3. That's the reasoning. Any questions on that? All right, so now the actual question said evaluate. So we could put here, it would have come out to about 3. Remember, it would never really reach it. It would just get closer and closer and closer and closer. Now someone might argue, well, but if you go all the way to infinity, wouldn't it reach it at infinity? You can't really get to infinity because it goes on forever. So it gets close to 3. We'll leave it at that. Now I'm going to do the same thing we did, except I'm going to draw it on the screen so you can see it as an asymptote. So let's type this in, except we're going to make that a variable. We're going to let it be x. This is a little tricky to type in correctly because I can't type it in 3 pieces. I got to type the whole thing in at once. So let's start with the numerator. 1 minus 1/3 to the 4th. All right, so there is my numerator, and I put the whole numerator in parentheses, so it's going to handle that as a group. I'm going to divide that by, and just to make life a little easier, I'm going to do this in my head. 1 minus a third is 2/3. Now, the last thing I have to do is double all of that. So I'm going to put another set of parentheses, and I'm going to stick a 2 in front of all of this. That's how you would type it all in at the same time. Now, I can check and see if we did it right, because I can go to my table, and I can let x equal 4, and see if I get 2.96. So let's go to my table. When x is 4, I get 2.96. When x is 5, I get, actually if I highlight it, you can see it, 2.962. Is that what I had? Nope, it should be 2.98. So, let me double check I typed it in right. Okay, I typed it in wrong. I told you we had to let this be a variable, and I didn't do that. So, we're not graphing it specifically for 4 or 5 or 6. We're letting it be x. Now, let's check it. So 4 is 2.96, 5, 2.9877, 6, 2.9959. Just double check. Perfect. So I typed it in correctly. How come if I type in like 25, it just says, oh, it adds up to 3 now? I said to you, you would never reach 3, but the calculator is showing a 3.
Because it can't graph an infinite.
Yeah, it can't. It's going to run out of room, right? It can't put 2.999999999. There's not enough room on the screen. So if I highlight it, okay, it says 3, but it's not 3. There's just so many 2.9 repeating that it's off the screen now. If you go a little bit lower, you might see that. Like that one says 3, but then if I highlight it, there you go. There's still enough room to show what happens if you add up the first 15 terms. But by the time you get to the first 25, there's too many 9s. Okay, it runs out of space. Okay, so we think it adds up to 3. So let's put a horizontal line at 3. And if we're correct, the graph in blue should look like it's getting closer and closer to the one in red, but it should never reach it. Okay, you'll see it in a second. So there's the graph in blue. Okay. There's the graph in red. And it actually looks like it reaches it very, very quickly. And they're so close together, it basically puts them on top of each other. But really, it's always just below it. Okay? That's what it would look like. Any question on that? Now, when you're looking at that graph, there's some things that don't really make sense. You'd never look at negative, the negative x-axis, because that would represent negative terms in the sequence. There's no such thing as a negative first term, negative second term. You start with the first term, okay? Or first term, right? So really, you should only look from the y-axis over. All right. So we already did this. Visualizing the sums, that's what I just drew. So in order to graph the problem we just had, this is exactly what I typed in. Okay, I had to use parentheses to make it work, right? Now, with x, I put this little note here. I said focus on the positive integer values of x. X represents the number of terms you're adding up. So why do you have to focus on integer values? Why can't x technically be mathematically x can be a decimal, but it wouldn't make sense for x to be a decimal in this problem. How come?
Power.
Well, powers can be decimals though, normally, but not here. What did I just say x represents?
How many numbers you're adding up?
How many numbers you're adding up. So
Yeah, a number.
you can't add up like 1.6 terms. You can add up 2 terms. You can add up 3 terms. You can't add up anything in between. There is nothing in between. So technically, that graph should look more like this as it approaches the asymptote. It should not be a connected graph. So the first dot would represent adding up the first term. The second dot would represent the first 2. The third dot, the first 3. The 12th dot, the first 12. But there is nothing in between the dots. Okay, that wouldn't make sense. So, any questions on why we should focus on positive integer values for x? There's no way for me to do that on the screen. I can draw it by hand like I just did for you, but I can't tell the calculator to do that. The calculator is always going to connect that line in blue, even though it shouldn't be. So what happens is, as x gets bigger and bigger and bigger, that's a good approximation of what it would add up to if you go to infinity. Okay. So we saw from the table, you didn't have to go that far. By the time you're adding up the first 4 terms, you're already at 2.96. That's pretty close to 3. Right? By the time you get to 15 terms, it already adds up to 2.999999997. So what we would say about this one is it converges very quickly. Very quickly, you can see it's going to add up to 3. It happens early on. All right, so we already did this. Find the sum using a graphical approach. So I'm not going to do the same thing again. Let's try this one. 4 times 3 to the k minus 1. So we're going to graph it. And remember, we're looking for something like this. Does it start to level off? If it does, then whatever it levels off to is what that would add up to. All right, so we need this formula again. All right. What's my first term here?
4. I mean, 4.
4. I told you the first term is sitting right there. And what's r? 3. So since I already have the last problem still typed in, all I need to do is change a couple numbers. And I can leave everything else. So change the first term. Well, let's get rid of that. Change the first term to 4. And now it's 1 minus r. Okay, r is 3. Technically, I don't need parentheses around the 3 anymore because it's not a fraction, but it's not going to hurt to leave them there. That's fine. So it's 1 minus r to the power, all divided by 1 minus r. 1 minus 3 is negative 2. Right? Again, I don't need parentheses around the negative 2. It's not going to hurt to leave them there. Since they were there, I just left them. So, any questions on how I just plugged those numbers into that formula? Okay, so let's graph it and see what happens. In fact, before we even graph it, let's just look at the table. All right, what was the first term in that sequence? 4. So if you add up the first 1 terms, what should they add up to? 4. And they do. Okay, let's find the second term by hand. Just make sure we kind of know what's going on. We already did 1. Let's plug in 2 for k. What's 2 minus 1?
2 minus 1.
2 minus 1.
1, I'm sorry.
2. No. 2 minus 1 is 1. What's 3 to the first power?
3.
3 times 4
12.
is 12. So the second term is 12. The first term was 4. What do you get if you add up the first 2 terms? 16. And that's what the calculator tells us. All right. Let's add up the first 3 terms. 52. The first 4 terms. 160.
What the heck?
If you add up the first 5 terms, 484. So what's happening?
It's increasing.
It's increasing. It's not getting closer and closer to anything. The terms are getting bigger and bigger and bigger as we go. So if we graph it, you're just going to see a curve that goes up off the screen as you head to the right. There is no asymptote there. It has to be an asymptote. In fact, I'll block off the negative part because you shouldn't even look at it.
Was there a horizontal asymptote? I mean vertical asymptote?
Nope. It's just going to go up forever. Eventually, the calculator is going to, well, I can't do anything until it stops. But once I get big enough, it's not going to be able to do it. So if I type in like 50, that's 1.4, and then there's 24 zeros after it. So it's pretty big. If I type in like 200, it can still do it, but I'm almost at the limit. The calculator can't do more than 100 zeros in the memory of the calculator. So by the time I get to 250, it's probably going to say error. Technically, it's not an error. It's just so big, it's off the screen. Okay. So that's not adding up to anything. It's not leveling off like that. So find the sum. There is no sum. Can't do that one. Now, when it did have a sum, we called it converged. It converged. Did anyone have a guess what you call it when it doesn't converge? The opposite of converge. Yes? Hannah?
I got nothing.
You got nothing?
Nope, not a thing.
A non-convergent.
A non-convergent. It was a movie with this word in it.
Inconverge.
Divergent.
Oh,
Oh, that's a
I was
good
gonna
book.
say that too. I thought about it. I was like, what sounds like converge?
So
Diverge.
in that example, as x got bigger and bigger, as we added up more and more terms, the graph did not have a horizontal asymptote. It didn't level off. We just kept getting bigger and bigger and bigger numbers. That kind of sum is called divergent. It diverges, or you could say divergent. So in that kind of problem, there's no numerical answer. If it converges, the way I would ask the question on the test is I would say, tell me whether the following converges or diverges. If it converges, find the sum. Okay. Now, you should be able to look at a problem and tell, without doing anything, whether it converges or diverges. You only have to look at one number, and that will tell you. Right, so we've seen some examples that converged. That was the first one I did. We've seen an example that diverged. That was the second one. Okay. You don't need to write that. Okay, I want to go back for a second and look at the one that diverged, look at the one that converged, and see if we can tell why. Okay, see if we know what to look at. Okay, so let's go back. So that diverged. 4 times 3 to the k minus 1. Let me put them on the screen at the same time. That one converged, the one on the left. That's the first one we did, and it added up to 3.
Multiplying by a whole number, it diverges. Multiplying by a fraction.
Yeah, all you have to do is look at par. In this case, r is a third, which means every time you add a number, it's 1/3 as big as it was before. So it's getting smaller and smaller and smaller. In this case, every time you add a number, it's triple what it was before. So the numbers that you're adding are getting bigger and bigger and bigger. So that's the only thing you need to look at to tell you if it converges or diverges. All right, so in the book, I'm not going to go through all of them, but they give you some different examples, and they ask you to see what happens if you let r equal 0.8, 0.9, 1.1, and then I think 1.2. So if r was 0.8, would that converge or diverge?
Converge.
It would converge, because each number you're adding is 0.8 times the last number. So it's a little smaller. So that would converge. How about 0.9?
Converge.
That would still converge, but what we would say is it converges a little slower. Because each number that you're adding is 9/10 as big as the one before it. So it's converging, but the numbers are not getting small fast. Okay? They are getting smaller, but not very fast. How about 1.1?
Diverge.
That would diverge. Each number is now 1.1 times as big as the last one. So it's a little bit bigger, not a lot, a little bit, but it's going to diverge. And 1.2?
Diverge.
That would also diverge.
What if r was 1?
If r was exactly 1, then we'd have a problem. If r was 1, what's 1 minus 1?
0.
Then you're dividing by 0. Now there's all kinds of problems. So we won't worry about what would happen if r was 1. Okay. Wouldn't you? Okay. So any questions on that? All right. So here's kind of summarizing what we just said. If r, or the absolute value of r is less than 1, so if you give me a value of r between -1 and 1, it will always converge. That's what absolute value of r less than 1 means. It's between -1 and +1. If you give me a value of r that's greater than 1 or less than -1, like -3, that's not going to converge. So we just said that r has to be a number between -1 and 1. So somebody give me a number between -1 and 1.
1 and what?
Between -1 and 1. 0.3. So r is 0.3. Let's raise 0.3 to the 5th power. Okay, let's see what happens. What's going to happen if you raise 0.3 to the 5th power?
It's going to shrink.
It's going to get smaller, right? It's going to be 0.3 times 0.3 times 0.3 times. It's going to start to get smaller. I get 0.002. Now, what if I did 0.3 to the 8th power? How is that going to compare to the one I just did?
It's going to be even smaller.
It's going to be even smaller. Now it's 0.0000065. Okay, just there's so many zeros it did scientific notation. So eventually, if I did like 0.0 to the 20th power, now it's 0.0 11 times and then a 3. What is this getting very, very close to?
0.
It's getting very close to 0. So the point is that in this formula, let me go back to the original one we had. Right here. If r is a fraction, okay, between -1 and 1, and you raise it to a really big power, this entire part basically gets very, very, very small. And it gets so small, it doesn't even matter anymore. And all you're left with is what's not crossed up. So when you add up infinitely many terms in a convergent sequence, That's what it adds up to. So it's an even simpler formula than what you had for finite, because I was able to cross something out. Now, if you try to use that formula on a divergent series, it has no meaning at all. It means nothing. You can do it, you'll get a number, but that number means nothing. So this formula is only important when r is between -1 and 1. In fact, we should probably write that. It's the only time you would use that formula. And this is for an infinite geometric series. Geometric series are the only type that can converge because you're multiplying by a number over and over and it's shrinking it. An arithmetic sequence could never converge, ever, if you add it up to infinity. Remember, arithmetic means you're adding the same number over and over. 6, 8, 10, 12. If I add all these up, are the terms getting smaller and smaller as I go? No. In an arithmetic sequence, they never do. Only geometric. So all arithmetic sequences are divergent if you add them up to infinity. All of them. All right, so let's look at this one. Now, let's pretend this was on the test. I would probably ask you first, is that convergent or divergent?
Convergent.
It's convergent. How do you know?
Because it says around.
Because what?
It's times a half.
Times a half. R is a half. So we know it's convergent. The other thing I need besides R, I need the first term. What's the first term?
5.
5. R is a half. Just fill in 5 and a half into that formula, and there's your answer. So we get 5 divided by 1 minus a half. What's 1 minus a half? A half. Be careful. What's 5 divided by a half? Not 5 divided by 2. 10. So if you were to add up every number from 1 to infinity in that sequence, they would add up to 10. There'd be a horizontal line at 10. Okay. Somebody give me a value of r that would make that diverge.
1.2.
1.2. It would diverge very slowly, but the numbers would be getting bigger and bigger. Yep. Any questions on that? No? Okay. Then that is the last lesson I will be teaching you in pre-calculus. That's it. All done. So that is your last homework assignment. 601, 21, 22, 29, 30. 33 to 35, that's all. 38, 39. 42 to 44. Okay, don't forget, I will be after school on Thursday if you need extra help. If you have anything to finish, it's got to be done by Friday or it's a 0.
We have a cheat sheet for that.
You can have a cheat sheet on the test, and remember your test is tomorrow. Okay, test tomorrow.